Okay, so the next part over here is to calculate the collector current. So the collector current is, and one thing about basically making these conversions is that basically, now of course you know that, for example, 0.1 amp, for example, 0.1 amp is the same thing as, if you convert this, you would get 0.1, for example, into, and you know that a milli is basically, a milli means 10 raised to the power negative 3, right? So, and that would be in amp. So this is 10 raised to the power negative 1, and so if I write this as 10 raised to the power negative 1, and 10 raised to the power negative 1, and 10 raised to the power negative 3, if you simplify, you will get a 1 over here, 10 raised to the power negative 2, basically over here, which is the same thing as, then bring this to the numerator, you get 10 raised to the power 2, and then you have milliamp over here, right? Which means that 0.1 amp is the same thing as 10 raised to the power 2, which is equal to 100 milliamp. Then basically you can, then if you basically make this 100 times smaller, meaning the divide by 10, you will get 0.01 amp, 100th of a milliamp. That's again the same thing as 0.01 times, for example, if you want to convert to milli, then you have basically, so you have milli over here, and 10 raised to the power negative 3, this is 10 raised to the power negative 2, and so if you simplify here, you'll get 10 raised to the power negative 1, and this is in amps. So this is the same thing as basically, this is the same thing as 10 raised to the power 1, which is equal to 10 milliamp, which means that 0.01 amp is the same thing as 10 milliamp. And by the same logic, then you can say that basically 0.001 amp is the same thing as 1 milliamp, right? So this is basically to calculate basically to convert between milliamp and amp, right? So that means that, for example, if you have if you know that, for example, 0.1 amp is the same thing as 100 milliamp, then basically 0.4 amp would be 400 milliamp. Because I multiply this side by 4, multiply this side by 4, I get this one. Or if I know that, for example, 0.01 amp is the same thing as, for example, 10 milliamp, then basically I know that 0.04 amp is the same thing as 40 milliamp, and so on and so forth. So this is simple enough. Then basically you can also develop some sort of relationship like this. I mean, when I was working in electronics, I used to know only this, because the only thing that I needed to know was conversion between amps and milliamps, and that was enough for me. So I didn't have to go any further from, for example, any further towards basically smaller currents. I was not working with them really. But now it's necessary for me and for anybody who wants to work with these transistors to be able to get into basically microamps, nanoamps, and so on and so forth. And so let's now calculate basically the same thing between amps and, for example, microamps. And of course, you know that, for example, you know that basically 1 microamp is 1 millionth of an amp, right? So you know that basically 0.0000001 amp is the same thing as 1 microamp. And then if you multiply this by 10, if you multiply this by 10, you will get basically, so multiply this side by 10, you'll get 10 microamp, and that's the same thing as 0.00004 zeros and 1 amp. This is of course not very useful, because you don't want to convert from amps to microamps. Most of the time you just don't need that. But we will use that in some other ways, meaning that in many situations it's actually beneficial to convert from milliamps to microamps. That sort of thing is necessary. So, and you know that basically then if you again multiply this side by 10, I will get 100 microamps, and then multiply this by 10, I get 1 zero less, one fewer zeros, and then that would be 0.00030 zeros and 1 basically amp, right? So this is how you would convert between amps and microamps, again, which is not very useful, but you, of course, you need to know that. Then you need to be able to convert between milliamps and microamps. And what that means is that, for example, you know that, for example, 1 milliamp is the same thing as 1 into 10 raised to the power negative 3 amps. Now, if you want to basically express this in microamps, you can simply write this as 10 raised to the power negative 3 into basically micro, and 10 raised to the power negative 6 in amps, and then you can simplify this as 10 raised to the power negative 3, and that's the same thing as 10 raised to the power 3 microamps, which means that basically 1 milliamp is the same thing as 1000 microamps, and therefore you can say that 1 milliamp is the same thing as 1000 microamp. And and then now let's see what is basically 100 microamp, meaning that you have to go in both directions, meaning that you have to go up and down. So you have 1 milliamp, you have 10 milliamp, you have 100 milliamp, and then you have to go down as well, meaning that you have to divide by 10. Divide by 10, you'll get 1/10 of a milliamp, which is 0.1 milliamp, and 1/100th of a milliamp, which is 0.01 milliamp. These four things you need to know, which means that basically we already calculated this. 1 milliamp is the same thing as 1000 microamp, if I'm not mistaken. So 1 milliamp is 1 into 10 raised to the power negative 3 amp, and 10 raised to the power negative 3 micro, 10 raised to the power negative 6. Calculate this as, simplify this as 10 raised to the power negative 3, and then that becomes 10 raised to the power 3 microamp, which is equal to 1000 microamp. That's correct, right? So then I can say that one milliamp is the same thing as 1000 microamp. 1000 microamp. Then basically you want to do these two and also these two as well. These are necessary, and then you can form a table of these, put them somewhere basically next to your electronics bench, or even when you're calculating next to your desk, and then use these conversion factors until you're proficient with them, and then you can get rid of the table if you need to. So then basically what you need to do is now we have calculated 1 milliamp, so that now let's see what is 10 milliamp. So 10 milliamp would be basically multiply this by, so if 1 milliamp is the same thing as basically 1000 microamp, then multiply this by 10 milliamp would be equal to 10,000 microamp. And then again, basically 100 milliamp would be equal to 100,000 microamp, right? So that is that. And then you can take the same thing and divide by 10, meaning that taking this and dividing by 10, I'll get 0.1 milliamp is the same thing as basically divide this by 10, you'll get 100 microamp. And then again divide this by 10, you'll get 0.01 milliamp is the same thing as basically 10 microamp. Usually these two are important, and probably sometimes this one, but these two are not that important. But then anyway, you want to keep all of this in a table and use them in your calculations, right? So you have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I write them all as a table. I'll write them all as a table, and then we will refer to them as we go along. So I save this somewhere on desktop, amp or current conversion 1, and put that on desktop somewhere. And these I already know, so I don't have to make a screenshot. So then if I go back to my desktop and go to current conversion, okay. So now what I will write them properly, meaning that we know that now basically, first of all, a 1 milliamp is the same thing as, we know that 1 milliamp is the same thing as basically 0.001 amp, and we know that 10 milliamp is the same thing as basically 0.01 amp, and we know that basically 100 milliamp is the same thing as 0.1 amp. That's basically one thing, that basically conversion between milliamps and amps. Moreover, you need to know that basically 1 milliamp is the same thing as 1,000 microamp. You need to know that 10 milliamp is the same thing as 10,000 microamp, and you need to know that 100 milliamp is the same thing as basically 100,000 basically microamp. On the other end, you know that basically 0.1 milliamp is the same thing as 100 microamp, and 0.01 milliamp is the same thing as 10 microamp, right? 10 microamp. So these are if you have these two conversion tables, you're good to go in almost all situations. And now I will make a screenshot of this and call it I call it, for example, current conversion, and put it on desktop. And there we have all that we need. And so, for example, now over here you can see that basically we calculated this current to be 0.10 raised to the power negative 1 amp, which is 1/10 of a milliamp, and 1/10 of a milliamp is basically 100 microamp. So 100 microamp we calculated here, so we didn't have to basically do all of that calculation. But one important thing that's basically that you need to take into consideration, if you're familiar with these conversion factors, of course you can use them intuitively and you will not run into any problems. Meaning that usually, basically we know that, for example, 1 kilogram is the same thing as 1,000 grams. So that means that then we know that half of a kilogram is half of 1,000 grams, which is 500 grams. So that sort of conversion we can do without making mistakes. But then sometimes the situation becomes the kind of situation which is confusing to me personally, because that's the type of situation I've not worked with enough in the past. And so in those kinds of situations I might make mistakes in conversion. And so in those sorts of situations, of course, there is always, the only way that works in all situations is using conversion factors. And what that means is that, for example, you're calculating you have basically 25 microamps. You have 25 microamps, and you want to express that in nanoamps, right? You want to express this in nanoamps. And these conversion factors, you can of course always get them on any introductory physics or chemistry book, or you can find them on the internet. So for example, you can go for SI conversion chart, and then you will come across something like this. So you can see that, for example, 10 raised to the power negative 9 is nano, for example, right? So you can have something like this. You can have some conversion table like this, and usually when you do a basic chemistry course and physics course, you usually basically put together a table for yourself in a notebook or in your notes, and then you already have this table in your notes, and you always use that. So basically what I mean is that basically these conversion factors you already have, you get them on the internet, you do something to get them anyway. But now, if you asked me to convert 25 microamps to, for example, to nanoamps, I don't know how to do that. I cannot calculate this in my mind, in my head. I just can't do that. So basically then you need to get your conversion factors, and micro is basically, based on my table, it tells me that micro is 10 raised to the power negative 6. Micro is basically the same thing as 10 raised to the power negative 6. And I want to express this in nanoamps. So nano is the same thing as 10 raised to the power negative 9. right? So what you need to do is that just use these conversion factors in order to basically convert this into whatever it is that you want to convert. So you write this as 25 microamps, and then you want to write your conversion factors in such a way that the unwanted things cancel out and the wanted things remain, right? So now, of course, I want to get rid of this micro because I don't need it, and I want nano to be instead in my expression. So I write this as, I multiply this by 25, and instead of micro, because I want to eliminate it, I know that micro is the same thing as basically 10 raised to the power negative 6, which means that this tells me that 1 micro is the same thing as 10 raised to the power negative 6. These are the same quantities. And this implies that, or this tells me that basically, this tells me that if I write 1 micro to basically 10 raised to the power negative 6, this is equal to 1. And also it tells me that, 10 raised to the power negative 6 to 1 micro is also equal to 1. It's like, for example, that the fact that, for example, 1000 grams is the same thing as 1 kilogram, right? These are the same quantities. They refer to the same masses, right? So which means that if I write 1000 grams divided by 1 kilogram, this is equal to 1, because this is the same quantity as this, meaning that I'm dividing, for example, the same quantity by the same quantity, meaning that I'm dividing 2 by 2. It's always equal to 1. So, and this also means that basically, 1 kilogram divided by 1000 grams is also equal to 1. Both of them are equal to 1, irrespective of the fact that whether you write them this way or this way, it's always equal to 1, because again, they are the same quantities. So when you have basically 1 micro is 10 raised to the power negative 6, so that means that they are the same quantities. That means that you can write this as 1 micro to 10 raised to the power negative 6 is equal to 1, and also 10 raised to the power negative 6 to 1 micro is also equal to 1, right? Now here I want this micro to be cancelled out, and this is a fraction whose denominator is 1. And I can basically, now I didn't really need to do this. So this is 25 micrograms, 25 micrograms. Okay. So now I want to get rid of this micro. So if I multiply this by, and I need to use either this conversion factor or this conversion factor. Now I need to multiply this by something, and that something needs to be either this one or this one. Now if I multiply this by this fraction, micro is in the numerator, I will get micro squared, which is not what I want. I want the micros to be cancelled out, which means that then basically I need to choose this in such a way that the micro happens to be in the denominator, which means that I will take this one. So I write 10 raised to the power negative 6 divided by micro, and then that way I will get a numerical representation of micro here in the numerator, and then the 2 micros will cancel out, right? By the same logic, basically what you can do is that now I want to express this also in nanoamps. I don't want to express it in amps, in nanoamps. So I know that basically nano is the same thing as 10 raised to the power negative 9. So which tells me that basically 1 nano is the same thing as divided by 10 raised to the power negative 9 is equal to 1. And also 10 raised to the power negative 9 by 1 nano is also equal to 1. Again, by using the same logic, because they are the same quantities. Now, since I want this to be expressed in nanoamps, the nano has to be in the numerator, because if I use, for example, this one, the nano would be in the denominator. I would have something like, for example, 25 divided by nano in amps, which is of course not I want. But if I use this thing over here, and if I multiply it by, for example, 1 nano to 10 raised to the power negative 9, now my unit becomes nanoamps, and then in the denominator I have the numerical representation of nano, which means that my numbers will simply be divided by 10 raised to the power negative 9, and everything works out fine. And then you can see that 10 raised to the power negative 6, 10 raised to the power negative 9, you can simplify. That becomes 10 raised to the power negative 3, right? And then basically, and then you have basically over here, you have this 10 raised to the power negative 3 can come, if it comes to the numerator, it becomes 10 raised to the power positive 3. If you have 10 raised to the power negative 3 in the denominator, when it comes to the numerator, the exponent changes sign to whatever, to the opposite of whatever it was. If it was negative, it becomes positive. If it wasn't positive, it becomes negative. And by the same logic, if 10 raised to the power negative 3 is in the numerator, if you send it to the denominator, again it changes sign. Whatever sign it had, or whatever sign that the exponent had, that sign changes to the opposite. But of course, the sign of the number itself does not change, meaning that you cannot send this to the numerator and write it as negative 10 raised to the power negative 3 or something like that. That doesn't mathematically makes no sense. But the sign of the exponent changes always whenever you send that exponent of 10 from the numerator to the denominator, or from the denominator into the numerator. Which means that the numbers that remain, the things that remain here, is basically I have a 25 and amp over here. So I have 25, and this 10 raised to the power negative 3 comes to the numerator, becomes 10 raised to the power 3. And then I have amp and nano here, so this becomes nanoamps. So this is 25 into 10 raised to the power 3 nanoamps, which is the same thing as basically 25,000, for example, nanoamps. And it makes sense because 20 micro is much larger, 1,000 times larger than nano, and then as a result, basically then 25 microamps would be the same thing as 25,000 nanoamps, right? Now, of course, this makes sense to me after I have done all of the calculation, but if you ask me to convert from microamps to nanoamps, I might actually make mistakes here, unless it's something that I have done enough basically in the past, and now I have gotten the hang of it, and then I can do the calculation with absolute certainty and confidence, and then that's no problem. But as long as you have doubt, or you don't have enough confidence in your calculations, you have to basically follow this conversion factor method, and it's very simple. You just multiply by some conversion factor that helps you with the conversion, and then eventually you will get to whatever it is that you wanted to, that you were basically looking for. So this was all about basic to unit conversion, which is of course very important in basically in physics, in chemistry, in electronics, of course. So then basically I know that my base current over here is 100 microamps, right? So now I can simply basically use the relationship between I of C and I of B and the beta of the transistor, I of B and the beta of the transistor, and I know that my beta is equal to 50 and I of C is equal to, is basically what I'm looking for, and I of B is basically 100 microamps. I just simply write it as 10 raised to the power negative 4 amps, and that basically means that basically I of C is equal to 50 into 10 raised to the power negative 4 amps, right? 10 raised to the power negative 4 amps. And therefore, basically, the conversion I leave up to you. I'm not very big on conversion. So I of C is equal to 50 into 10 raised to the power negative 4 amps. But of course, then you have to follow one system, meaning that this number is, I mean, the way that I have written it is neither scientific notation, nor is it based on the convention that we have in electronics. So in scientific notation, basically this part of the number has to be some number between 1 and 10. It has to be some number between 1 and 10. It cannot be some number like 50. It wouldn't be scientific notation. And of course there is reasons for that, because it doesn't fit with the whole system, and one of the goals of the scientific notation is that basically then you know about the number of significant figures. Now if I wrote my number this way, then people will get confused, meaning that this way there is no way to know how many significant figures my number has. Is it 1? Is it 2? There is no way to know. Now, for example, over here, assuming that, for example, based on the numbers that we have here, for example, you can see that this resistor has only one significant figure. Or, for example, and so since it comes into calculation, then everything that you calculate will eventually have one significant figure. And so I will I will have to express this number in one significant figure only. Which means that I will write this number, I can write this number as 5 into 10 into 10 raised to the power negative 4 amps. Which is the same thing as basically 5 into 10 raised to the power negative 3 amps, right? Which is basically 5 milliamps, right? So I write this number as 5 into 10 I of C. I write it as 5 into 10 into 10 into 10 raised to the power negative 3 amps, which is the same thing as 5 milliamps, because milli is 10 raised to the power negative 3. Now this number that I have written here is actually in scientific notation, and what it's supposed to mean is that basically this number has only one significant figure, not more than that. If I were to show that, for example, this number had 2 significant figures, if I were to show that I of C is equal to 5 into 10 raised to the power negative 3 amps, if I were to show that this number had 2 significant figures, I would write it as I of C is equal to 5.0 into 10 raised to the power negative 3 amps. If I were to show that this number had 3 significant figures, I would write it as I of C is equal to 5.00 into 10 raised to the power negative 3 amps. And basically one significant figure means that basically I have actually I have measured this current all the way up to the last 1 amp. If I write it as having 2 significant figures, that basically means that I have measured this number actually all the way up to 1/10 of an amp, meaning that I'm certain about this number all the way up to 1/10 of an amp. If I wrote this number as in this, basically in this orientation and in this way, that means that I have measured this number all the way up to 1/100th of an amp, and these are all measured digits, and meaning that I'm certain about this number all the way up to 1/100th of an amp. And then if you gave me this number, now what I know is that, so the person that wrote this number down, so they have measured this current all the way up to 100th of an amp. So I have that much certainty about this number, so basically that's how I'm going to use the number in my work or in my calculation and so on and so forth, right? But then the number shows how much certainty you have in your number, meaning that, for example, sometimes on your voltmeter you read the voltage and you have basically for example, after the ones place value you have 5 digits. You just ignore those digits because you don't need them in that particular work that you're doing, and so the rest of the digits you have just simply thrown out. You have ignored them. And then once the digits are lost, they are lost forever, unless you make the measurement again, of course. So this is about scientific notation, right? Now, so this is about that. So my collector current is now 5 milliamps, which means that 5 milliamp is going through this resistor. So now I can calculate the voltage drop across this resistor, meaning that if I basically apply the Ohm's law to this resistor, R is equal to V times R is equal to, or V is equal to I times R. V is equal to I times R. I have basically the voltage drop across the resistor is equal to the current going through the resistor, which is 5 into 10 raised to the power negative 3 amp times R, which is the value of this resistor. R of C is 1 kilo ohm, 10 raised to the power 3 ohm, and then you can cancel these two out. That is V is equal to 5 ohm amp, which is the same thing as V is equal to 5 volts, 5 volts. So your voltage is 5 volts. That means that V of R of C, that means that V of R of C is equal to 5 volts. Is equal to 5 volts. Now again, you need to, of course, always analyze your circuit and see what you're doing. So you have your power supply here, comes over here through this resistor, through the PN junction, and back to the negative pole of your power supply. You have something like this. You have something like this. So there is, and this is your power supply V of S, 10 volts, and the voltage drop across these 2 points is basically 5 volts. That means that the voltage drop across these 2 points, V of C, if you add these 2 voltages together, that should be equal to the supply voltage. That means that V of C plus 5 volts is equal to 10 volts. That means that V of C is equal to 10 volts minus 5 volts. That means that V of C is equal to 5 volts, right? And so that means that V of C is equal to 5 volts, meaning that with this configuration of these resistors and the power supply voltage and everything that you have here, half of the power supply voltage is dropped across this resistor and the other half remains over here for basically and will be dropped across the PN junction, and that becomes your output voltage for the circuit, right? So that was basically question number 7 in the book. Now let's do a couple more of these questions, and we will then basically move to the next chapter of the book. Okay, so now let's do a simple experiment, and hopefully if I have the, lately I haven't had much, I haven't had much chance to work at my electronics bench because mainly I have nothing to do and I don't want to sit and do, well, this kind of experiment. It would take only 5 minutes and then I have to come back to this desk. So I haven't really done much in practical on my bench, but hopefully if we have the opportunity, I will also show you all of these on the bench, meaning that I'll show you, for example, and of course you're supposed to do the same thing on your own, meaning that you have to experiment with all of these things. Otherwise, everything that I know about electronics, which is not much of course, but well, I used to work in electronics. I used to have a successful business in electronics, in repairs and that sort of thing, and installation, programming, telecommunication systems and that sort of thing. Everything that I know about electronics is based on experiment. When I was a kid, I used to do all kinds of experiments with batteries, with lamps, with resistors, but of course I never got into transistors. I didn't really need to know how these transistors work. And then later on, we got into radios. Cordless telephones became very popular like 20 years ago, and we were of course we were supposed to repair them. So then that was basically where I couldn't do much in cordless systems, because when you don't know how the system works, you don't know how to repair it. And then so basically then whenever something came up, for example, we had a customer and they brought a cordless telephone in. There were actually two types of telephones. They were short-range telephones and long-range telephones. There were all of these telephones telephone systems that it was a cordless telephone that you could take with you, for example, 10-20 kilometers away from the base unit, and then still you could make a phone call. And back then in Iran, there was still no cell phones. So basically this was like one of the greatest breakthroughs in the whole country, because now you could take your telephone with you. This is like what happened in the US, for example, in the 1960s, 70s or something like that, when the cell phone slowly came in. So then, basically, long story short, we had to be able to repair these phones, and the number of these phones was large. I mean, everybody was buying one of those phones, and they were called Nokia, and they were based on, I mean, the name was chosen based on this brand of Nokia cell phones that were prevalent back then. Nokia 5110, 6110, and something like that. It was a handset for cell phones, actually. And so they then they had built these cell phones, and they have designed the handsets basically in the same way that Nokia had designed their handset. But then there was this big, this long antenna on the top of the cell phone, and then you had to extend that antenna in order to make a call, and then you had to basically put it back when your call was over. So then basically, gradually I became interested in radios, and I just wanted to know how these radios work, which is of course a fascinating thing. And then now 20 years later, I decided to basically learn everything there is to learn in order to understand how these radios. And of course, you have to understand, for that you need to understand the whole physics, the whole chemistry, the whole mathematics behind that, the whole electronics behind that, and then you'll be able to understand how telecommunication works, how wireless telecommunication works. So now let's meaning that basically my whole point here being that basically experimenting is actually very it could be very beneficial, meaning that everything that I know about electronics, about electricity and that sort of thing is basically related to back then when I was experimenting. And I started experimenting when I was 5-6 years old, and I never stopped until I was 20, 18, 16, 18, 20, and then I started working. So now, so we will do a couple of experiments. I have a simple electronics bench. We will do all of these. Of course, it's going to be hard for me to remember what to do, what not to do. But then we will find our way through these experiments as well. Now, let's do a simple theoretical experiment. They call it dry labbing, meaning that you're labbing, but you're dry labbing, meaning that you're not getting your hands wet. So let's now do basically, let's make some changes to this resistor here. Now this is basically chapter 3, the end of chapter questions, question number 8. And now let's change the value of this resistor to the base resistor to 200 kilo ohms, from 100 kilo ohms to 200 kilo ohms. And when the resistor was, when R of B was basically 100 kilo ohms, you saw that basically V of C was equal to 5 volts, right? So we already calculated that. Now, what you can expect here, and this is something valuable in electronics, of course, that you know what's going to happen as a result of what you do what you change in a circuit, and that's basically the whole of electronics. So when I increase the value of this resistor here, assuming that there is no voltage drop here between the base and the emitter of this transistor, the voltage across the resistor remains the same because you're not changing the power supply. So once basically based on the Ohm's law, your V remains unchanged, and your R is now your V is constant. Since your R is basically increasing from going from 100 kilo ohms to 200 kilo ohms two times increasing, then you can expect that your current is going to be, the base current is going to be cut in half, right? The base current being cut in half, the collector current is going to be cut in half, right? So now the collector current cut in half, the voltage drop across this resistor is, again, you can calculate it using V is equal to IR. So again, the voltage over here is constant. It's not, I'm not changing that. The current cut in half, and basically the voltage drop over here, the voltage drop over here, if I were to calculate that, the current cut in half, that means that for basically, and the resistance is constant here. I'm not changing this resistor here. So if the current is cut in half, then of course, based on this algebraic equation, you can see that the voltage has to be cut in half as well, because of the algebraic relationship between Vi and R. Keeping R constant, if you cut the current in half, you have to cut the voltage in half as well, otherwise it wouldn't stay in equation, right? So that means that basically previously the voltage across this resistor was 5 volts. Now the voltage cut in half would be 2.5 volts. That means that the rest of the voltage dropping across the collector emitter junction of the transistor would be 7.5 volts, which is 7.5 plus 2.5 is equal to 10 volts, which is the whole power supply voltage. Which means that if I'm expecting that if R of C is if R of B is changed to, I'm expecting that if R of B is changed to 200 kilo ohms, that basically V of C would be equal to 7.5 volts, right? That's what I'm expecting here. So let's see if that's true. We will do the calculation one more time and see if that's basically the case. And what we did here right now to calculate this voltage is called qualitative analysis. So qualitative analysis, meaning that you don't really care about the quantities that much. You just want to know what happens in the circuit when you do a certain thing, right? So we will do that in the next video. We will do now some calculations in order to calculate basically the voltage at this point, V of C, when R of B is increased to 200 kilo. So I'll see you in the next video, and thank you.